Mora, and this presentation is about.
It is better?
Well, I work for Pauscherer Institute in Switzerland, and the title of my presentation is Simulation of Crack Propagation in Thick Wall Cylinders using XFEM. This is the outline of my presentation. I will give a short introduction of the problem, then the material, the models in FEM and XFEM, results and conclusions. So what is the problem that we have? We want to predict the crack propagations and crack arrest in RPB steel. So in normal conditions, the RPB is at high temperature and high pressure, but when an accident occurs, like a loss of coolant accident, the pressure decreases rapidly and also the temperature due to the cold water that is injected, and in a presence of initial defect, like an initial defect, this can produce crack initiation if there is enough embrittlement of the material due to the mutant embrittlement. So in these conditions, in the worst case scenario, we could have crack propagation and failure of the vessel that we don't want to have, of course. So in the motivation of this study was to initially design small specimens in order to make experiments and see what happened in reality, and also like track the crack propagation. But and this is because in the real we cannot perform the experiments in a real scale reactor, and the idea to use a mock-up or a small specimen is to represent similar conditions in terms of the thermal stresses and fractal toughness of the material. So the reduced problem is like a state here, so a pre-cracked cylinder or mock-up in which the pre-crack can propagate. And for that, in these contributions, we took the results for FALSAR 1 and 2, and we applied the normal XFEM implementation in Abacus. So in order to illustrate more or less what happened in FALSAR, I put this slide which shows the beginning of FALSAR in 1994, and they used these two types of cylinders, these initial effects, this material. This cylinder shows under pressure and temperature rather ductile behavior. So they in FALSAR 2 include this another material that shows at that time more brittle behavior of the crack propagation. In this PhD thesis in MPA in Stuttgart, they use one single material because in this case they use two materials, and they just use one single material and track the crack propagation. So I will take this as like my reference solution for this study. So what is the integrity, or how is the integrity assessment done in RPVs? So basically we assume an accident, so a PTS, and include an initial defect, but the point in this kind of analysis is that the assumptions are very conservative and doesn't account on uncertainties. The analysis is divided in different steps, as you can see here: thermohydraulic analysis, structural assessment, and fracture mechanics. And based on this analysis, we can plot the stress intensity factor of an initial defect and compare this one against the fractal toughness. And we can have different situations, safe, unsafe, or safe if we consider warming pre-stress effects. But in our case, we want to go to the crack arrest analysis, meaning that we want to initiate the propagation of the crack and see what happens if we can observe crack initiation and arrest in our simulation, because it's already observed in experiments. So this is the geometry of FALSAR Kelm specimen. So it has 800 millimeters outer diameter, 400 millimeters inner diameters. This is the weight, 2.3 tons. And this is the material that we'll talk about that a little bit later. And they include a fully circumferential crack. The loading conditions are here. So we have a constant inner pressure of 5 megapascals, and actual preloading of 15 meganewtons. And cold water is injected on the cylinder, which is preheated at 250 degrees Celsius. So this is the material. I took it from this reference. So these are the mechanical elastic properties, temperature-dependent elastic properties, and these are the physical properties. And basically, this material is a modification of the 17 molybdenum vanadium A4. It's a special heat treatment, and the heat treatment is done in order to obtain a high ductile to brittle transition temperature of 250. This is the model, the FEM model. So as XFEM in Abacus is restricted only to plane strain or plane stress cases and also 3D cases. So we decided to use as cycling symmetry. So basically this allows us to use 3D elements, and of course we have to change the type of element depending on the simulations that we are doing. So for the thermal analysis we use this type of element, and we change it for the mechanical analysis. Also we have to change it again for the fractal mechanics analysis. The loading conditions are described here. So we applied a thermal shock in the inner surface as indicated this plot. Adiabatic conditions in the outer surface. The thermal shock follows this table. So basically we have the temperature of the fluid and the heat transfer coefficients, and the inner pressure that I said before is 5 megapascal, and a self-preloading. Additionally, we include boundary conditions in the middle plane in order to avoid body motion. So this slide just briefly describes the implementation of XFEM in Abacus. Here in Abacus you can use XFEM for stationary cracks, in which the crack can be located wherever in the element, like it's shown in this diagram, and it accounts for the full enrichment. And also you can use it for propagating crack, but in the case of the propagating crack, the crack has to cut the element. The crack tip is forced to lie in one of the edges of the element, and the asymptotic near tip singularity functions are not included in the enrichment scheme, and only heaviside functions are included. So basically this is the descriptions of this displacement field in case of XFEM in Abacus. We also need for the XFEM model the initiation of the propagation criteria. So we consider only pure mode 1 as the maximum principal stress. And in order to make it dependent on the temperature, we relate this using linear fracture mechanics with the refractive tolerance that we already know. We need also these parameters. We assume for now 300 microns, but we have to perform the experiments and try to figure out or connect this with the microstructure of the material. For the crack propagations, we relate the energy release rate with the fractal toughness of the material, and we contemplate two cases, one considering constant energy release rate, and the second case is temperature dependent energy release rate. So this is how the fractal toughness looks like for the material already with the modifications. We can describe this fractal toughness with the SAME curve, which is given by this expression, and basically we set to the ductile transition temperature 250, and this is how it looks like the model, the refined area where we include the initial defect. This is the size view, this is the top view, so you can see like the smallest light we consider is only 1 degree, and we have here like zoom in the crack region. The initial defect has crack depth wall thickness ratio of 0.1, meaning that the initial defect has 20 millimeters, and we use for now regular meshes. So these are the results in terms of temperature and stresses without the crack. So here in green we see the fluid temperature, in red the outer surface, the inner surface temperature, and the outer surface temperature in blue. And these are the stresses history for the radial, tangential, and axial stresses. So we observe that also here are the contours for temperature and stresses in different times. and we observe that they are above the yield stress, and this is because we are considering only linear elastic properties of the material, and which is a kind of rather fair assumption in this case, because we are dealing with a hardening material due to the Newtonian radiation, hardened materials. And the maximum stress is expected around 100 seconds after the injection of the water. So these are the experimental results as reported in the thesis, in the PhD thesis. So they have an initial notch, a fatigue crack, and then they observed 9 cracks arrest during the PTS. And the crack propagation shows at the beginning transgranular failure with conductivity that we ignored also in our model. So this is the COD, this is the average because they reported in different locations. So this is basically the average in time. And this is what we use as a reference solution. These are the descriptions of the mesh, and we use 2 different meshes for now. One with 500 microns, the average size, and the other one is 250. And basically, in the case, we consider for the damage evolution a constant value of the energy release rate. Obviously, the crack propagates entirely along the thickness of the cylinder. So this plot compares the COD of the simulations for the 2 different sizes that we consider in the element and the experimental result. So the next step that we did, or the next analysis that we performed, was to change the energy release rate, and we make it dependent on temperature. And here you see the contours of the temperature and the crack propagation. So here already at 100 seconds, you see that the crack is already at the very hot part of the cylinder. Well, here the crack propagation is controlled by the temperature profile. Here we compare the simulation with the constant value of the energy release rate, and here is the temperature dependent value and the experiment. So we see that more or less in the case that we consider temperature dependent properties, refractory properties, we are able to approach the experimental solution. So it seems like it's more realistic. So in summary conclusion, we simulate the crack propagation on a wall-thick cylinder subjected to PTS. We use XFEM as is implemented, no changes there. And we assume axisymmetric case because of the explained reason. So the defect practically closes the specimen when we consider constant energy release rate, and we can control the growth of the crack when we consider temperature-dependent properties. The criteria for initiation was based on the lower bound of the fractal toughness, so we didn't consider the scattering fractal toughness. This is a very conservative approach. As you know, this has a very high scatter. And for the future work, we are planning to do thermal shock experiments on mock-ups, small mock-ups, in order to find the parameters needed on the model, and try to also do again the simulations on these small specimens, and also investigate what happened with the scatter and the fractal toughness. And with this, I thank my colleagues, Marcus Niffenegger and Rajul Mao, and you for your attention. Thank you very much.
That's a very nice presentation. The floor is now open. Yeah,
I have 2 questions. In the simulations, the crack don't go along a straight line.
No.
But it's a fully complete axisymmetric problem. Why do they deviate from this? My second question, and my first question, second is, your criterion for crack growth, it is based on some maximum strength. Why didn't you use the J integral, which is calculated automatically in abacus? It compares this with the local toughness.
Okay, well, the first question, I suppose this crack deviation is because, as far as I know, in case of a crack, the crack can't bifurcate, no? The problem can bifurcate, and somehow, a small numerical problems can happen and deviate the crack, no? As far as I understand the problem. So it's rather related to the numerical solution, I would say. And yeah, and the second question is why we use the local stress is because we believe that we can characterize whether this parameter than the others. And the J integral, I think you can calculate it, but for static cases only now, at least as far as I understand. I'm not sure if you can really calculate it.
Considering also just the brittle material, he said that it's already hardened. So that's why I suggest
you can calculate J integral from there, you can transfer it to K1 values.
Sure.
Yeah, also.
I think it's the way XFEM works. I think XFEM, the way the crack is introduced in XFEM, that gives out the fracture toughness, and I think that's the only way that cracks can be. It's mesh modification method with actress, isn't it?
In Abacus, they calculate the K factors, is it in combination with XFEM?
Yeah, but for the stationary cracks, I would say. For the propagating crack, you
So
do not
yes,
really-
you're right. For the propagating, they do not. But it is a...
You didn't speak too much about the material properties. You assumed an elastic material, or
Yeah, for now we assume just elastic properties.
Okay. I would propose to use elastic plastic materials, and the material properties should also vary depending on the temperature.
Yeah.
And then you have also resolved the problem with your critical distance. Because then you could say, okay, I take a critical distance that is the magnitude of the process zone, which depends on also on the loading or on the...
Yeah, you are completely right, and we are
yeah.
working on that direction. That's why we already have the material, because that was the tricky part for the experiment, to get the material, because it has a very high TBTT, and that's not easy to fabricate, so to manufacture. So now that we already have it, the idea is to go into this direction.
Okay, and did you have experimental data about the crack extension?
Sorry, say that.
Do you have experimental data about crack extension from the old PhD?
Yeah, it is one. Yeah. So this is the test.
Yeah, but I see only a COD. It's something like the crack mouth opening displacement or so, but not the
They just report, well, the only thing that they report
only
is
segment,
bridge work.
okay.
So also, like, if we are able to perform experiments, we can also store more data about the crack propagation.
I suggest a comment, suggest both to what Sane and Ortmars. So you could have easily calculated the size of the plastic zone, and then it will be easier answer, so just whether you can stay within the domain of the geoelastic analysis. So I definitely would consider elastoplastic analysis for 250 degrees at this level, but okay, it's your future work.
Yeah.
I guess you have to check the energy release rate in all directions also to choose the path, right?
Yeah, for now we are considering node 1, so we didn't care about the other nodes, but yeah, for sure, yeah. Depending on our observation in the experiments, probably we have to consider more.
Does it work with an Illumi type of mesh, irregular mesh?
Well, I didn't try till now.
If you did, then it would have the opportunity to avoid the straight crack path. If you have a straight crack, you have a very stiff material here. It becomes unstable at some point and goes this way.
Okay,
But I think in finite element it still goes just straight, or could.
thank you.
If it's okay, thank you very much.
The safety can be great in space.
Now, it's time for